by NASA, and it involves Court Strong and Jay Mace, as well as myself. And we have our lead author here, Sha Lee, is the graduate student who's been doing most of this work. Okay, so to motivate this, we have observations show that once a lead opens, it starts freezing over pretty quickly. And we're often thinking that leads are open water and the open water leads to clouds, but because there's thin ice that rapidly covers leads, then we really need to consider what the effect of this thin ice is on the transfer of moisture and heat. So this chart here is showing what happens in a simulation, but when we essentially close a lead or refreeze it, the heat fluxes over the open lead are, in this case, about 350 watts sensible heat and latent heat about 100. Once we freeze this over, in this case, we just instantaneously do it and put about a 1 inch, 2.5 centimeter layer of ice on it. Then the sensible heat flux drops a little bit to 275, but the latent heat almost disappears. And so the question is, what is the impact of this lead freezing on low clouds? Because open leads will produce clouds, but what happens once the lead freezes? So we did some simulations with a cloud resolving model. On the left side, show what happens. The lead is in the middle of this 50-kilometer domain. And this is a cross section. And the cloud condensate is shown in the red. So you see a prominent plume of cloudiness downwind of the lead. This is a wide lead in this case, about 4 kilometers. Once we freeze the lead, you see that the cloud that is now wrapping around the domain, once it reaches the lead, is dissipated. It does not persist. So the thin ice actually acts to dissipate the cloud. And the reason for this is that essentially we've converted our lead into a source of heat and moisture to just a source of heat. And now that is desiccating the cloud, it's drying it out. We have a convective plume over the lead, which eliminates the cloud. Okay, well, is there observational evidence of this? Okay, here's our conclusion. Observational evidence. We compared, I'm looking at my time here. I see I have 1.5 minutes.
Yes, that's right.
We compared low cloud occurrence over the Beaufort Sea north of Barrow during periods of large lead fraction from AMSR E, and their lead fraction includes open water and thin ice. It doesn't discriminate the two. And we compared the large lead fraction times to periods with small lead fractions. We considered similar meteorological conditions, ridge northwest of Barrow with northerly flow over the study region. So this type of flow basically doesn't have low-level clouds in it unless they're just in a very thin layer. We don't have deep precipitating clouds. And we used both ground-based cloud radar from the ARM North Slope of Alaska site and also CloudSat to look at the cloud occurrence frequency profiles. And here are the results. On the low lead flux days, shown on the left, we have the fairly high frequency of low clouds. That's just the peak at the lowest levels below 1 kilometer. And then on the high lead flux days, the cloud occurrence is less. And this is counterintuitive. I mean, when we started this, we thought we'd see just the opposite. And we also have similar results from CloudSat here. And that's it. 1 second left.
All right, perfect.
No time for questions, though, of course.
Oh, I know we can spend a minute on questions.
All right.
It looks like Heis has a question, and he's typed it in the chat box. He says, the conditions that result in leads, high wind stress, also will result in larger turbulent fluxes, but the lead may persist beyond the winds. How sensitive are the results to the wind speeds?
Well, we just categorized our regimes by meteorological condition. So we didn't sort it out by wind speed. So we don't know that.
Okay, that's good. Just 10 seconds. So what do you think is going on? why is there fewer low clouds?
Oh, well, basically because we turn the lead into a source of heat and moisture,
Right.
into just a source of heat. So it becomes a moist plume, and now it becomes a dry plume. And it's a dry convective boundary layer, which entrains drier air from above.
Okay, and you're killing the
It's not
clouds.
cloud. Yeah,
Yeah.
it's not the clouds.
Okay, very nice. Lauren Zamora, you are next.
Okay.
And it's a satellite-based estimate of aerosol cloud microphysical effects from combustion aerosols over the Arctic Ocean.
Okay.
And so, Steve, if you will click the red stop share button at the top of this, there we go.
Okay. Can you see my screen?
We can.
Great. All right. So I just want to first thank my collaborators who are listed here below, and also my funding source, which is NASA. So yeah, we're interested in understanding aerosol cloud microphysical effects over the Arctic Ocean. And these can impact, or rather these can affect cloud particle size, precipitation, lifetime, freezing, which in turn affects cloud fraction and phase, which in turn affects moisture distribution, energy balance, and future climate. And we know that aerosol effects can be large, but they're also very uncertain. And here's just an example illustrating that. So this is data collected from CloudSat. It's the surface longwave cloud radium effect. And this is during polar night. We looked specifically at polar night because during that time, aerosol direct and semi-direct effects are minimal. So you can see there's actually a really big difference in surface cloud radium effect when in these two cases, first where column model black carbon is in the lower quartile, and also and compared to when it's in the upper quartile. And just for reference, this is the sea ice extent during wintertime. And on average over sea ice, there's actually a 10 watt per meter squared difference in surface long wave cloud radium effect. So that's really quite large. And so if this were caused by aerosols, we'd expect it to be seen over sea ice because, or at least more prominently over sea ice, because that's where the atmosphere is more stable. So for example, just shown on the bottom left here, that's lower tropospheric stability over open ocean and sea ice. So it's higher there. But we also know that meteorology co-varies with aerosols. And I don't have time to show it here, but in particular, relative humidity varies with aerosols. And so the question is, how much of the signal is from aerosols and how much is from co-varying meteorology? So from a generalized additive model, we were able to show that meteorological covariation can actually explain most of the signal. It's somewhere between 57 and 91% of, at least of cloud fraction differences. But that said, aerosols could still explain up to 40% of the differences, so they can't be discounted. So we were trying to understand more specifically what are the actual aerosol effects. So what we did to reduce the meteorological effects were to first bin the data into relative humidity and temperature bins. So here's an example from nighttime Arctic at an altitude level between 0.6 and 1.5 kilometers above the sea ice. So you can see we sorted the data into temperature and relative humidity. And in this case, we're looking at cloud fraction changes and the differences between all clouds and the clean cloud subset with respect to combustion aerosols. And we see there's predominantly blue colors here. In this case, that means that there's less cloud cover in average compared to clean condition, or average conditions compared to clean conditions. So we did that for a variety of cloud properties. So then we take the weighted mean property changes, and we can see that across the Arctic, horizontal cloud fraction is actually 6% smaller on average than in clean conditions. Also, ice phase at this particular altitude is 7% more likely to be in the ice phase, and precipitation frequencies clouds are 3% more likely to be precipitating. So this is at one particular altitude level. We did this for a variety of other altitude levels and found at low levels trends are similar at at low clouds and also over open ocean. So this suggests to us that combustion aerosols help glaciate low liquid-containing clouds, which are actually quite common in the near surface Arctic. But interestingly, we see a different trend at higher altitudes. So this is, for example, 6 to 8.5 kilometers above the sea ice. And this is, again, cloud fraction change. So the weighted mean indicates that it's a much smaller change. So we see, but that it's significant. So we see a 0.4% increase in cloud fraction, and they're 0.3 less likely to be precipitating. But what's interesting here is that all of these clouds are ice. So we have some evidence to suggest that aerosols are actively influencing ice crystal formation or other properties in high altitude ice phase clouds, as well as the mixed phase clouds. So to summarize, we know that these aerosol mediated effects on clouds are hard to distinguish from covariant meteorological factors. And we saw a 10 watt per meter squared long wave surface cloud rated heating difference at high versus low modeled combustion aerosols. And we think that meteorological covariability can actually account for much, but not all of this signal. So the implications are, first, that when we have changes of temperature and relative humidity of air masses entering the Arctic, that will likely have a larger regional influence on cloud fraction than the microphysical effects of the aerosols themselves. But that said, the aerosols shouldn't be discounted, particularly because they're significantly associated with effects on freezing processes, probably, over the Arctic Ocean. Is that my timer? Okay. All right, I'll leave it at that. Thanks.
So, any questions for Lauren?
My poster's on Monday, if anyone wants to come see it.
So Monday morning, is that means?
Yes.
Okay. And Daniel, I have you next. Daniel Feldman.
Oh.
I don't have your title handy, but we're going to see it here in a second, I guess.
Great. Okay, can you see my screen?
We can.
Okay, great. So I'm going to be presenting on a near-term fix to and a long-term challenge with modeling Arctic infrared radiation. There's the near-term fix is a poster on Friday, and the long-term challenge is an oral presentation also on Friday, both Friday morning. Okay, so first the fix. The ensemble of climate models shows a persistent cold pole bias that crops up, especially in the winter time. This has persisted between CMIP 3 and CMIP 5. We'll see what happens with CMIP 6. Since it's in the winter in the Arctic, it's at least not directly related to surface albedo effects, and could perhaps arise from infrared radiation. So we did a survey a few years ago of a number of climate models and noticed that the way that they were handling infrared radiative processes, especially surface emissivity, the spectrally resolved fraction of the of radiation that is emitted that differs from an ideal black body, is not as physical as it could be, as well as long wave cloud scattering. Those are not generally included in climate models, and so these sorts of processes might become more important as high latitudes in dry high latitudes. So what we did is we modified the Community Earth System model and put in a database of realistic surface emissivity. So what we see on these figures here is that we can actually largely resolve the December, January, February surface temperature bias with respect to ERA, the area reanalysis. And that's what the figure on the left shows. The middle figure shows the bias of the large modeling ensemble of CESM. So this is kind of the out-of-the-box version of that model. And on the right shows the difference between the two plots, which pops up primarily in the Arctic Ocean. And so basically realistic emissivity can largely resolve these biases, largely a sensitivity test. of the models to this radiative process. And you can see this paper for more details, but it's an exciting possibility that this could resolve cold pull biases. The challenge that we noted is a talk on Friday morning. We wanted to indicate that the seasonality of surface radiation is really quite important for Arctic amplification. A recent paper showed that there's a kind of a complicated mechanism between local and remote effects that can contribute to Arctic amplification if they're not properly modeled, and infrared radiative fluxes can matter for this. So through a wide variety of observations, primarily we looked at the data from the Summit Station in Greenland, and we found a curious result here. We saw that actually we looked at the infrared radiative observations and saw that the surface radiative forcing, which is basically the amount of energy being added by greenhouse gases, carbon dioxide and methane, is out of phase with the gas concentrations. And we were able to show that this is a result of the fact that these are sensitive to atmospheric thermodynamics, which dominates over ice sheets much more than the gas concentrations. And the reason this matters is because in the future, this phasing of the radiative forcing might actually change. With rising greenhouse gas concentrations, the amplitude of the seasonal cycle will grow quite dramatically, and also the phase might change. And what this means is models are going to have to do an increasingly better job at predicting temperature and moisture just to capture the direct effect of rising greenhouse gases. And if they don't, their biases are going to grow with longer integration. So please see that, see the presentation for more details. Ultimately, I'm really excited because we're at a golden age, or on the precipice of a golden age for Arctic infrared radiative observations through a wide variety of ARM and satellite campaigns. And so we can really test all of these really largely amount to sensitivity studies with data from ARM campaigns and pre-fire and forum as they come online.
Okay, that was perfect timing. Questions? No questions for Daniel. That was nice. That was another counterintuitive result from Summit Greenland and the direct radiative forcing of those greenhouse gases.
Yeah, but we're able to explain it with, you know, when we did a signal decomposition analysis, and you know, we looked at the thermodynamic sensitivity. It really does line up.
Yep.
So.
Nope, that's great. All right, Max Maahn.
Yes, hello.
Colorado Boulder, spatial dependence of cloud properties at the north slope of Alaska.
And so Daniel, if you'll just click the red stop share button. Max, you should be able to share your screen.
Okay. Can you see my screen now?
Yes, we can.
Okay, so this is about the spatial dependence of cloud properties in northern Alaska. And we're looking at a region at the Beaufort Sea in northern Alaska around Oliktok Point, which is one of the ARM facilities in Alaska. And it's actually two studies in one. So the first topic is we look at the spatial variabilities from a scanning cloud radar. So we have this cloud, sorry, this cloud radar here located just at the shore at Oliktok Point. And this is the 20-kilometer range, the coverage of that cloud radar. So the question is, how are cloud and precipitation properties different over the ocean than over the land? So we gridded all the data for 1.5 years. That's the maximum time we had the data available. And interestingly, of course, you have to filter by surface type, because you can imagine this forcing is very different when you have sea ice and snow in comparison to open sea and bare soil. So on the left side, we have summer conditions, meaning we have open ocean and bare soil. And you see, I hope you can see that there's a black line here, which is the coastline. And you see that we have a lot more cloud, and actually I should say precipitation observations, because this requires at least drizzle in the cloud due to the sensitivity of the radar. So this is either more drizzle or more ice clouds in the southern part where there is bare soil in comparison to the open ocean where there is less observations. If you compare that to autumn conditions, meaning we have, sorry, that was the wrong directions. So on the left side, on the first one, as said, bare soil, open ocean, but there was always when there was solar radiation available. And you can imagine at these high latitudes, there's a long polar night. So if you don't have solar radiation available, this image flips. So this is same surface conditions, still bare soil and open ocean, but now without solar radiation. And you see now we have actually more clouds over the open ocean. And if you look through the different scanning angles of the radar, you can actually see that this is far further, rather shallow clouds in contrast to the larger, mostly deeper clouds during the day. The second part of that study is looking at the whole northern slope from MODIS. And for this, we regridded 10 years of MODIS data for this domain. And why did we do that? So there's the Prudhoe Bay oil field, which are these black dots on this map here, which are all the petroleum wells. And the question is, how does this source of local pollution, how does it change cloud properties? Because the rest of the North Slope of Alaska is barely touched by humans. So there is Barrow, which is another settlement, but otherwise there's barely any human influence. And if you regrid MODIS data and average for 10 years, we see here the effective radius. You see that actually we have a contrast over ocean and over land, which is actually mostly because the sub data sets are different. MODIS has trouble with the low sun angle at these high latitudes and with the effect of bright surfaces. So you can actually only compare ocean to ocean and land to land. But if you compare land to land, you see that here in this orange triangle where most of the oil ways are located, we see this depression in effective radius consistent with what we expect from more cloud condensation nuclei. So this is liquid clouds only, I should say. And I mean, then we see this plume here. And when we filter this data set and look only, take only data where the main wind direction is coming from the northeast, then this effect is getting stronger. I see I proceeded by accident already to that slide. So this is with the main wind direction. This is without the main wind direction. You can see that this kind of plume is getting more pronounced. So we are confident that this is really associated to these local pollution. Also because the at least the part west of 146 degrees is fairly flat. There is no terrain. It's just ponds and tundra, so there's no reason why there should be any orographic impact. Also, so if you want to learn more about that, my poster is Friday morning. And just to summarize, we see at fairly small scales changes due to the land-sea difference. With scanning cloud radar and from MODIS, we see how local emissions change liquid cloud properties.
Thanks so much, Max. That's a really exciting result. I forgot all about the Prudhoe Bay oil and gas activities up there. Any other questions for Max?
Max, this is Patrick. You mentioned about how the clouds over the land in summertime were thicker and there were thinner clouds that were over the ocean in autumn. I was wondering how thick were those clouds in summertime versus the thinness of the clouds over the ocean in fall?
That's an excellent question, but we have exactly two available beams for the radar. So we can probe the clouds only at 3 degrees and 5 degrees. So at a radius of, I don't know, 10 kilometers, that's something like 1 and 2 kilometers.
Okay.
So I don't know. That's,
okay. Thanks.
All right. Next we have Jessie Creamean. from Colorado State University.
Okay, can everybody see my screen?
Yes, we can.
Okay, since I did not provide my title, I have an invited oral presentation on Monday on this particular topic. So it's looking at biological processes as a source of warm temperature ice nucleating particles in the Arctic Ocean. So basically I went on an icebreaker expedition during the summer of 2017, and I'm calling it a NARCO-1, so ice nucleating particles over the Arctic Ocean. And basically it entailed leaving the Aleutian Islands, sailing up through the Bering Strait into the Chukchi Sea region, and then coming back down during late August to mid-September. And so the objective of the study was to evaluate sources of marine aerosol found in the lower atmosphere and the potential of those aerosols to modify Arctic cloud ice by serving as ice nucleating particles, or INPs. So we had a number of measurements on board, and those include collection of seawater samples. And so we did some offline analyses of INP concentrations and also some DNA sequencing to look at the biology of those samples. And so in this map, every one of those large dots that you see, that's where we had a daily seawater sample taken from near the surface. There were also measurements of different aerosol properties on board. So in real time, we had information on aerosol number concentrations, size, mass concentrations, and then also chemistry, including some trace metals. And then there was a number of collectors on board that gave us information on daily size result aerosol that we then processed offline for INPs, for total aerosol chemistry and morphology. And then we also had samplers on board that collected on Petri dishes so we could culture for bacteria. And this is mostly because we have different types of particles that are good at nucleating ice, and those mainly being biological particles, but also mineral dust. And so we use this combination of information to hone in on the identification of INP sources and the resulting climate impacts. And so I'm actually going to show no details on the results or methods really, but kind of give you a synopsis of this phytoplankton bloom case that we observed in that Bering Strait region. So this is a really simple schematic going from south to north, from the Gulf of Anadyr, which is basically south of Siberia in that region, the Bering Strait in the center here, and then the South Chukchi Sea. And so basically we used a combination of the INP measurements, of chemical oceanography, of biological oceanography and physical oceanography, and also atmospheric dynamics to really put together this story for this case that we observed. And so we had this, from the Gulf of Anadyr, we have this really cold, dense, nutrient-rich water that comes into the Bering Strait. And these nutrients really fuel phytoplankton blooms that can happen in the Bering Strait region. So these little critters here you see are phytoplankton. And we have a sharp picnic line in this region. So that is basically like the boundary layer in the atmosphere. It serves to prevent the surface waters of the ocean from mixing from the bottom benthic layers closer to the sediment. And so what happens is these nutrients aren't reaching the bacteria that reside in the benthic or sediment regions. And so we don't see a lot of bacteria proliferating right here. But as we see the water that's moving through the Bering Strait region, it slows down because it's not being funneled through a tiny strait. And it also becomes nutrient limited because the phytoplankton are eating up any of the nutrients from that Anadyr water. And so the phytoplankton stop proliferating. They tend to die off, and then they sink in this deposition zone that's just north of the Bering Strait. And so that actually is what feeds the bacteria in this region. And during our specific case, we saw this wind-driven mixing in this region. So it's a pretty shallow region. It's about 50 meters deep. And so this mixing happened from both winds going opposite direction of the currents. And so this actually brought the bacteria up from the bottom of the ocean to the surface, where the winds were able to transmit them into the atmosphere and where they were able to serve as ice nucleating particles. So we found these warm temperature bacteria, ice nucleating particles, in the surface waters of the ocean, but also in the atmospheric samples that we collected. So if you want to find out more information, feel free to come to my talk on Monday. I think it's the second afternoon session.
Sorry, I was muted. That's perfect, Jessie. You still have 40 seconds.
All right. I'll take any questions then.
Yeah, time for questions. That's a great story. And I love the happy and sad microbes.
So
Patrick,
Jessie, oh, sorry.
No, go ahead.
Oh, sorry. Jessie, so you said that you found those bacteria. Were they actually serving as ice-nucleating particles?
So we don't know exactly what the INPs were, but because I didn't show the information here, but because of the biogeochemical signatures that we saw in the surface waters, we think what we were seeing were bacteria. And based on the whole body of work on ice nucleation of phytoplankton versus bacteria, the range in which we saw the particles form ice was what bacteria typically form ice at. So we don't know for sure, but we can kind of speculate what they were, and we think they were bacteria in this case.
Okay, thanks.
Mm-hmm.
So Heist de Boer has a comment, interesting result. How persistent is this pattern? Can we see any cloud response from satellite observations?
So in terms of this particular year, this bloom was very persistent in the strait. So we sailed north end of August and south again in the middle of September, and it was still pretty prolific. So in terms of that time of year, it was a pretty persistent bloom. With that said, we sailed the same area in 2018, and we didn't see that bloom in that location. It was actually a little deeper in the water, but I still have to look at those data to see if we can see anything above the surface there. But I haven't looked at satellite data to look at clouds from that region, but I actually do have a student who is working on that climatology of clouds in the Bering Strait and Chukchi region. So
great, very, very exciting. All right, Patrick Taylor from NASA Langley. Oh, go ahead.
Sorry, I think Daniel might have had a question.
Yeah,
Oh, go ahead, Daniel.
I was just wondering if you could see it from, if there's an ocean color signal associated with these blooms?
yes, so you can see it. The problem is a lot of times that region's really cloudy. So it's difficult to really look at high time resolution images of it. But like for instance, my student is looking at monthly chlorophyll concentrations in that region relative to the cloud properties. But yeah, you can see chlorophyll signatures from like MODIS.
Excellent. All right, Patrick Taylor, first remind us of the title of your talk and...
Sure thing. The title of my talk is Understanding the Controls on the Arctic Surface Energy Budget and CMIP-5 Model Biases. So I don't have this in my talk anywhere, but I have a poster on Friday morning, so hopefully I'll see you guys there. So the surface energy budget in the Arctic is really an important feature of the Arctic climate system and has a huge impact on how it evolves going forward, not just impacting surface temperature, but also having a huge impact on sea ice and how it evolves going forward. Just as a quick back-the-envelope calculation that I did, if you look at the biomass data set, it shows that we're losing on average about 310 cubic kilometers per year of sea ice volume. And you can explain that by roughly in 0.2 watt per square meter surface energy imbalance. So it's small numbers of surface energy budget, small changes in the surface energy budget can have pretty big impacts. And so if you look at these charts that I have here, these are showing you the errors or the biases in CMIP-5 climate models across the Arctic, averaged over the Arctic cap north of 60 degrees relative to the series surface energy budget values. And you see that climate models struggle to reproduce the observations. And in particular, there are a few that I want to point out here and then talk about in a little bit more detail. And the first one on the left chart here showing the long wave surface fluxes. This red line shows you the all sky downwelling long wave radiation. The fact that this red line is well above zero here shows you that Ceres has much more downwelling long wave radiation to the surface than the CMIP-5 climate models. And this is the ensemble across about 24 climate models across the Arctic. And so there's wintertime, very strong, there's too little, let me say it this way, there's much too little downwelling long wave radiation from the CMIP-5 models. Another really important error bias that I'd like to discuss is the fact that this red line, which is the downwelling shortwave radiation in summer, Ceres has much more downwelling shortwave reaching the surface than you find in the CMIP-5 climate models. So climate models, the CMIP-5 models struggle to represent the mean state character and the characteristics of variability of the surface energy budget. So we look at this in the past in some papers in 2016 and others, just on a mean basis to try to see, you know, across the Arctic and even in certain regions, how do these mean biases look? And there are a lot of shortcomings with that because it's very difficult to identify which processes may be driving these errors. So what we've done here is to try to take the next step, which is to apply an atmospheric regime kind of decomposition methodology, which will allow us to identify which specific atmospheric meteorological conditions the climate models are struggling with the most. So for this, we've done this using a couple different variables, but here I'll show our atmospheric regime methodology using lower tropospheric stability, which is defined as the potential temperature difference between the surface and 700 hectopascals, and then 500 hectopascal vertical velocity. So the top two plots here are showing you the relative frequency of occurrence of all of these bins. And so we see that the most frequently occurring bins in wintertime for MERA 2 are this about -4 hectopascals per day, which is weak subsiding motion in the mid-troposphere, and then lower tropospheric stability values between 22 and 26 or so Kelvin. If you compare that to what the CMIT 5 climate models show, you see that there's this big red colors are showing you that CMIT 5 models have a much higher frequency of occurrence than what you see in the MERA 2. So in wintertime, CMIT 5 models tend to have a much more stable lower troposphere. If you then compare that on the right panel, which is summertime, you see that the CMIT 5 models kind of show a broader distribution. And so in analyzing the climate model biases in this way, we hope to isolate which conditions kind of climate models are struggling with the most. So just to highlight those, the two that I mentioned a couple slides ago, first for the wintertime downwelling longwave bias, again, the models tend to have too little downwelling longwave to the surface, which may contribute in part to the bias, that the cold surface temperature bias that Dan was talking about earlier. If you look at this across all of the regimes for all sky downwelling longwave here, you see there's this, this blue color pretty much everywhere. Some these regions on the left part of the plot showing you sinking motion, those seem to contribute a little bit more, but it's not a huge signal anywhere. But if you break this out into the clear sky versus the longwave cloud radiative effect contributions, so there's some really interesting things that you can see where here in the middle of the plot shows you the regions that are happening most frequently, where in fact the clear sky biases, I'll finish up on this slide then, the clear sky biases actually are higher than series, so it works opposite than what you see in the downwelling long wave. But you see the cloud biases in this case then are slightly compensating. But one of the really interesting things that we found from this is that the long wave cloud effect, while it seems that overall, when you average over all conditions, the models have too little cloud warming at the surface due to enhanced downwelling long wave radiation, but you see that under substance conditions here in strong lower tropospheric stability, the models actually have a much stronger surface cloud radiative effect in series. It seems to be these large-scale ascent regions that the models struggle with the most. So I'll leave it at that, but I have a few more details that I would love to share with you guys at my poster. Thanks.
Okay. Why don't we have everyone remind us again when their poster / presentation is? Patrick, you said yours was Friday?
Friday morning.
Okay. And then we'll start again at the beginning with Steve.
He's dropped off.
Okay. And Lauren, yours is?
Mine's Monday morning.
Okay. And Daniel?
Friday morning for both the poster and the oral talk.
Okay. And Max?
Also Friday morning.
Okay. I wonder if some of you might be in the same session. And Jessie?
That's true.
This one is the second afternoon session on Monday.
Okay, Monday afternoon late. Okay. Yeah, Steve had to leave. So Heiss is telling us, thank you. There's a town hall, IASC.
That's IAS. It's the International
Arctic.
It's the international coordinating body for a lot of the Arctic Science Committee. Yep.
The International Arctic Science Committee town hall is Monday evening, and IARCPIC has a town hall Wednesday at lunch. I'll be able to go to that. You guys are welcome to stop by. Or if you see me or Heiss or Jen Mercer's one of our new coordinators from NSF. She's a good person to know. Again, we try to have folks that are involved with the long-term planning and the funding decisions for the agencies as part of the leadership of these coordinating teams. One of the other things that we skipped today was sort of announcements. With AGU coming up, that was sort of the big thing, but if there's any other community meetings that you guys know have recently been scheduled so that we can put them on our calendar, or if there's something you are organizing, now's a good time to tell us about it.
I'm not organizing anything, but I'm aware of a Arctic aerosol-cloud interaction workshop that's going to take place in the UK in April.
Okay.
Centered on specific to the Arctic. It's called Quiescent. I'm not organizing it, but I'm going to be there. So
Great. Send that to Meredith, and she'll post it on our Arctic website and put it on our notes.
It looks like Heiss has sent that
Okay.
already
Okay.
in the chat. You said I'm just making sure it's the same one in Cambridge.
Yeah, that's right.
Okay, great.
Oh, yep. Heiss has it. Same one. Okay, good.
Thanks.
Still, it's good to announce it since some of us may have missed it. Any other? I know that NASA is working on a call for, it's probably going to come out in March. Well, in February, our Roses call is going to come out for the year. And there's going to be some things that might be applicable. I might be able to highlight it at another meeting, but something new is that we're going to have some funding for the planetary boundary layer characterization, both temperature, water vapor, and also aerosol. And part of this call is we're looking for a science team members that want to help write a white paper. So there's some funding in there for people, but as part of this effort, we're going to have a workshop, and we hope to provide some funding for people to attend the workshop. The dates haven't been set, but you'll see more about this probably in March. But just something to keep in mind.
So Barry, I also wanted to chime in terms of other meetings.
Yes, go ahead.
Yeah, so it also in Cambridge, you can one in July, and I'll send this on to the group, but there is the decision meeting for whether or not the European Space Agency's Forum mission moves forward, which would be measuring far infrared radiation. That takes place in July, and I believe that's open to the public. And so it's actually a competition between Forum and another instrument called SKIM that measures ocean currents.
Great. We still have a few minutes. I was going to mention that NASA has a workshop in Pasadena at the end of July. Let me just pull up the dates. It's for the aerosol-cloud convection and precipitation satellite mission. And it's, where is that request? Let me look it up on my calendar because I have it there as well. So it's a community workshop. So it's open to everybody. We're going to be working on, well, you'll learn more about the mission, but we're going to be working on the science traceability matrix. So it's the 29th and 30th of January, and it's at the Pasadena Hilton. I'll send information to Meredith, and she can post it. But this is basically the follow-on missions for Calypso and CloudSat. And someday on a future IARC will have the some of the members of the leadership of this group talk about what's going to be, or maybe we'll have them talk about what was discussed at the meeting, either before, well, anyway, there'll be, but anyway, this is open to the public. It's, I don't think there's any funding for folks to attend, but it's something that if you're happen to be in the area or maybe someone you know lives there would be able to tell you more about it. I'll be there.